Thanks for waiting for me.
Of course.
Sorry I was late.
Yeah, no
probably.
problem.
I told you guys that I am available at 6, right?
Yeah.
Sorry.
Yeah, I announced it for 10 p.m. UTC, so we accounted for this.
Okay, sounds good.
Okay, so we can start. I'll share my screen. Oh, I can't share my screen because.
Sorry, let me do that. While I'm doing the co-hosting thing, just to mention, like I just realized that there is this thing I said about scaling category theory and spaces. There is actually a point on a chapter or a fragment in page 7 of the Joyal text called "Are topoi really spaces?" And he makes exactly the same claim.
So that's where you got it from.
Yeah, that's where I probably read it there, and then I pretended that it was my idea. But it's backed up by none other than Caramello's nemesis.
Yeah, but I mean, the idea has been around, right? It's this synthetic spaces, like Leibniz thing that we talked about before.
Yeah.
So, but yeah, made more, let's say, rigorous now.
Yeah, but I think that the problem with Leibniz is that you still have monads, right? Before spaces. So like you can talk about relational spaces, but you do presuppose ontologically that there is something prior to this that is like a unity. You don't start from like nothing and then you get to construct intrinsic properties of spaces based on relations. Like there is an idea of a thing that is a relation, right? Which is the monad and stuff like this. So anyway,
yeah.
Relation.
I mean, no wonder that's the point of reference in this chapter.
Yeah, exactly. It was a good segue, in fact.
Yeah.
Talking about that.
Yeah, talking about that. So, last time we covered a lot of ground. I was watching it again at certain points, and I realized like maybe it wasn't super clear in some areas. So I wanted to do a brief review, just on a couple of points. Also, to kind of get us on the same page again for the category theory to come. So I know last time we talked about relations, and I wanted to show this picture as a way of kind of helping us understand why relations have something to do with this product construction here. Because last time I was saying that relations have something to do with the morphism to a product, right? Something like that. And I think that wasn't very rigorous or easy to understand even. So in here, you can see I have a row and a column of elements. They're the same. So X by X here. So X is a set containing A, B, C, D. Mm-hmm. And you can see that the reflexive relation cuts across because A is related to A, B is related to B, and so on. C is related to C. And then symmetric is this like purple one, right? If A is related to C, then C must be related to A. Mm-hmm. And then transitive can then be seen as a triangle here. Like if you have two, like A is related to B, B is related to C, then therefore A must be related to C. So this kind of gives you a nice
that's really cool
visual representation, of the properties that we talked about here. And then you can see D has no relation to anything else except for itself. Mm-hmm. So that clarifies one thing. And then I added some points here. So originally I said that a relation is a morphism from some random set, not random, but arbitrary set to the product X by Y, and it allows you to select ordered pairs. So if you imagine X by Y to be this type of table here, the morphism will choose the relations, right, by hitting the points that are related. So in this case, there's 10 points here, right? So our set A would have 10 points, and then the morphism would select these 10 in the product. So that's one way to think about relations as morphisms, but it's not the standard way in category theory. and this is because of the notion of composition, which we want the composition of categories to, or morphisms, at least, to correspond to the transitivity of relations here, which is why the option number 1 here is not the standard way, right? So this is what I presented last time.
Mm-hmm.
I provided 2 other ones. The second one is the preimage of any function gives you an equivalence relation given by whenever 2 elements are sent to the same element on the codomain, then they are equivalent,
Mm-hmm.
they're related, right? So this is another way we can think about at least equivalence relations. So here, yeah, so like a simple example here, right? This is an equivalence relation because this is the preimage here is exactly 2 sets, this one and this one,
Mm-hmm.
right? So we've already partitioned a space automatically whenever we have a function like this, even if it's injective, right? If it was injective like 2 to 2, then it would just be 2 classes of elements here, each containing only 1. Okay, so that's number 2, a preimage as a relation. And then number 3 is the one that's standard in category theory, which is to say that a relation is any morphism from X to Y, where if X is related to Y, meaning an element of the domain is related to the element of the codomain, that means that this relation has sent X to Y, right? So in this case, yeah, X is in something, and then it gets sent to Y. And this is, and there's a bunch of other things getting sent to other points. Here, this would be a relation. And the utility or the benefit of this third definition is that we can then compose. So X is related to Y, Y is related to Z, and then composition will tell us that there's some function. So if this was like F and G, right, this would be G follow F. So we automatically get this transitivity here. So that's why point 3 is the one, option 3 is the one that's used. Okay, so yeah, just clarifies that, because we will need relations later on again when we talk about when we get to sheaves and so on. So let's move on to.
And I think also it's important because this is not what we will see in the chapter on relations, right? I mean,
yeah, that too. So we need to also be careful to understand relations in the mathematical definition, mathematical sense, as different from how Badiou presents it. Yeah, because Badiou basically uses relations as functions between sheaves. So his notion of relation is that, but at the same time though, this third option kind of applies to his thing as well, because even in Badiou's definition of relation, you get a composition,
mm-hmm.
right? If object A is related to object B in a world, and object B is related to object C, then object A will be related to object C. So you have this same structure. So that's a good point. Yeah.
Yeah, but I mean, it will be this plus some restriction, right? Which is the preservation of some characteristics. But
yeah, not anything can be related to anything else. It will require extra structure preservation. Yeah.
I think that this is the part of the book that he most wants to kind of annoy contemporary philosophers, because you get to a chapter on relations, and there's such strong kind of talk on relational ontology, and even if the book is pretty much about relational spaces, right? When you get to relation, he gives it it says relations is like this conservative thing.
Yeah, exactly. Relations are very, the way he portrays them, they're very very conservative. They preserve things, but actually that is in line with how mathematicians think of morphisms, right?
Yeah.
Morphisms can never give you more information than what's in the domain. They just, they're either injective, or meaning they preserve information, or they are surjective and then they lose some information. But the ability to lose information doesn't prevent us from creating new constructions on the basis of that relation, which is the interesting part. Like in this example here, we have monotonic functions, right? Monotonic means it preserves order. So in that sense, it doesn't really add anything new. At best, it's an isomorphism. So you just mapped one order relation onto another equivalent one, right? So like 1, 2, 3, A, B, C, right? So yeah, I mean, order preserving doesn't seem like that special, because this is an isomorphism. But then the interesting part is when you have order preserving but non-isomorphic functions, right? So actually, because it's a partial order relation. Yes.
I can understand the link, because I know that there is a sequence, 1, 2, 3, A, B, C. If I didn't know that ABC is a sequence, I could infer that thinking about the relation between the letter and the number, because the thing is, when we have this kind of interaction, if I can call this interaction, those interactions, they just don't change the functions inside that different spaces in interaction, isn't it?
Mm-hmm. Yeah, they lose some information, but they preserve some other information, and that's the important part. In this case, nothing is lost, right? This is an isomorphism, so at least we can say in terms of order, nothing is lost here. But an example of something that preserves order, but still loses some information, would be this one, right? So this is a non-injective or non-mono monotonic function, right? In other words, and the reason this is because our relation in question is less than or equal to.
You said non-injective but a monotonic function. That's
yes, point. Exactly. Non-injective but monotonic.
But to preserve, I mean, can something be monotonic but only to one point of the codomain? Wouldn't we at least need two?
No, because this relation is reflexive. So this, let's call this A. Well, we've already said that A is less than or equal to A.
Yeah, I see. Okay, so that's right. Because actually preserves. Okay.
Yeah. So 1 is less than or equal to 2. 2 is less than or equal to 3. But A is less than or equal to A. So if you mapped everything to one thing, it's kind of trivial because you lost all the differences in your domain, but you did preserve the relation.
Mm-hmm.
So this was something that wasn't very clear in the last presentation, but this fact allows us to collapse things, right? And still maintain order. So it gives us a certain flexibility.
Okay.
Yeah. So that's an important point. And yeah, in general, this idea of losing some information but keeping some other information, that's actually how we explore these spaces. And by spaces here, I mean not the space of the domain or the codomain, but the space of the functions between them, right? The space of transformations. That's what we're trying to investigate. In this case, we have like C and D here, which have some certain structure. And we want to ask, can we define an adjoint given the red function? So remember last time I had a lot of trouble pinning down the notion of adjunction. And even afterwards, I was trying to play with this structure to see when we do get an adjunction and when we don't. So I came up with these two examples, but it would be good to explore and try to find other examples. But in the left case, there is no adjunction, right? And why is that? Because adjunction here means it has to satisfy these rules, either this rule or this rule. Okay, and one way to think about this rule is to say that, so f of c is the, let's say, the target of the red arrow. D is something that is just in D, right? Some element of D. So this is saying whenever the tip of the red arrow is less than or equal to some element, so in this case, this is less than or equal to itself and also to this topmost circle, right? There's only two that it's less than or equal to. Then if you have an adjunction, you have to follow the other arrow back, and whatever that hits must be greater than where you started, greater than or equal to where you started. So that's what the R of D is here. Right? So let's think about this for a moment. If we were to choose for this element in the D, yeah, I really should have called D, it should be C because it's a codomain, but yeah, let's say D, this set D here. If I choose an arrow from this to, let's say, this one directly to the left of it here, that won't work because of this arrow over here on the left, right? Because this arrow here says f of c is less than or equal to d. However, it is not less than or equal to. So the source of this arrow is not less than or equal to the target of R. So let me draw this. Maybe it will be clearer. I can do a simpler version actually. So
let me clarify just a little technical thing. By your account, the little c and little d in the formula are constants. They are not variables. Or are they variables?
They're variables. So whenever the case, maybe like C can be anything.
Okay.
In the C, like
in the C,
domain, in the big C, right? Yeah. So let's just do a simpler example here of a subset of this problem, right? So what I did here was I drew two red arrows from the bottommost, so like this, right? Just confirming that this is, okay, so first thing we need to do is we need to confirm that this arrow, we call it F, which takes everything in here to some stuff here, right? Confirm that F is monotonic. Okay, so this bottom element is less than these two elements, right? Let me add the arrows here. And this bottom element is sent to this element. Well, we know that this element is already less than or equal to itself. So it's okay that I also sent its parent here. It's greater than to be over here as well, because like, let's say this is 1, 2, 3, 4, A, B, C, D, right? So B is less than or equal to B, right? We know that. 1 is less than or equal to 2, and 1 is less than or equal to 1. So it's okay that we send both of these facts here because the less than or equal to is preserved, right? So we're collapsing in this case, but it's okay. Now, 3 is less than or equal to 4. Oh, also, yeah, 1 is less than or equal to 3. And that's maintained, right? Because 1 is sent to B, 3 is sent to D, and B is less than or equal to D. So that this one is also okay. And then 3 and 4 is also okay, right? Because we said collapsing is okay. Okay, so we've established with that F is monotonic. Okay, but why is there no adjunction possible? So let's. So again, we did this, and then, oh, sorry, no, not. We did this, right? So an adjunction means now we want to make a new arrow from here to here that's also monotonic, such that it satisfies this condition here. So perhaps I should see if I can copy and paste this. Is that alphabetical? I can't read the script. Okay.
But I read it fine the way it is.
You read it, okay. Okay. So yeah, we want to make an arrow back here that is also monotonic, and because of that, we're constrained, right? We can't, for example, I can't send this top element back down here, right? Because, well, let's say more obvious example, I can't send it down here necessarily because then I wouldn't be preserving the order.
Mm-hmm.
Unless, oh, actually what I could do is I could send everything down here. That would be monotonic, right? We said that collapsing preserves monotonicity. But why is this not an adjunction? Because whenever the white arrow hits this thing, if we trace it back, it must also be less than or equal to where the red arrow goes. So here's an example of, we'll call it from, again, 1, 2, 3, 4. So, and then A, B, C, D. So we're looking specifically at 2 to B, right?
Mm-hmm.
2 is mapped to B. And then B is mapped to 1. But this doesn't fit this example because f of C in this case, so f of 2 is B. So let's write that f of.
No wonder you couldn't find another example.
Yeah, it's once you see the pattern, it becomes a little more. Yeah, but it's not a trivial thing, right?
Yeah.
So f of 2 is B. Right, and then and this is okay, right? So we're still okay because B is less than or equal to something here, right? So in this case, B is less than or equal to B. However, what is C here? C is 2. And what does B get sent to? 1. So let's use this. R of B is equal to 1. And then, right, 2 is not less than or equal to 1. Okay, so let's try to generalize this. This is a very specific case. What I'm saying is for any targeted object, so B is a targeted object because their arrow is pointing at it, right? I follow the arrow back to its source, which is 2, and I check that this 2 is less than any red arrow coming out of B. In this case, the arrow coming out of B is 1. It goes into 1. And 2 is the source of the arrow going into B. And 2 cannot be less than or equal to 1. So this is not an adjunction.
How about we collapse on 4?
What if we collapse on 4? So everything goes to 4?
Mm-hmm.
Yeah, that's a good question. So if everything goes to 4, that's also not an adjunction because let's try this. Because we have to do it the other way around as well, right? So let's choose.
Yeah, that makes sense.
Yeah. Like this, right? Okay, again, we choose a target and we go back along the target. And we notice that this is not less than or equal to the original target.
So would you say that, intuitive definition of injunctions is that you're comparing two inverse monotonic mappings and seeing if they preserve structure between them and not between the domains?
You mean the two functions are preserving something between them?
Yeah, like you have a function on one way,
Yeah.
you have a function the other way, and then you want to see if they both overlap at some level of ordering information, in this case, for example, right? Like they don't need to be mapping to the same things, like to be inverse of each other, but they still need to be in such a way that the information that one preserved, for example, from the numbers to the letters, that information that was preserved is coherent with the inverse map that doesn't necessarily preserve the ordering in the same way, but the two maps need to have some relation that is
the relation. So the relation between the maps is just this thing, right? This equation.
Yeah, that's what it's guaranteeing, right? It's not guaranteeing that things were mapped like inverse. So if 4 was mapped to D, D is mapped back to 4. That's not really necessary to get a jump.
Yeah. Oh, yeah. No. It doesn't have to be known.
Yeah. So it's a weaker version of this inverse mapping, right?
I would say it's something more, right? Because I mean, it's not supposed to be an inverse mapping. I mean, it's not just that it is a weaker version, but it's precluding an inverse mapping, right?
No, because if everything went injunctive, like 1 to A, 2 to B, 3 to C, and 4 to D, the inverse would be okay.
Yeah.
It would be okay, but it wouldn't be an adjunction, right?
I would be. And actually, So this is an interesting point. An inverse is both a right and a left adjoint.
Yeah.
Okay.
It has both properties. So this is what I was saying last time about splitting a concept in two.
Yeah, that's my point. Like
because what I understood is that the splitting is a necessary condition to be an adjunction. This was what I understood, but it seems that the splitting is not a necessary condition. The splitting is a necessary condition to be either a left or a right adjunction, right?
Yes, to be left only or right only, you're splitting in that sense, yeah. But the inverse itself has both properties.
Okay, fine.
Yeah. And we can kind of see that by like looking at the property of, again, what we said before about if, in the definition of a monotonic function, right? Let's use C less than or equal to D implies that f of C is less than or equal to f of D. This is the monotonic condition.
Mm-hmm.
So if you just convert this to using the inverse instead of f, you can derive this thing to show that, right? So
can you read it? I can't read it. Can you read it again?
Let me write this again. Is that visible?
Yeah.
Yeah. So we want to turn this bottom thing to this top right thing to show that the inverse is the
Stronger
is also
case. Yeah.
an adjunction. Yeah, it's a case that can be transformed into that case.
You showed the red thing is satisfying the first line. Now we want to show that the pink thing is satisfying the second line, right?
No, I was showing that the red does not satisfy.
No, sorry, I mean white. White is satisfying the first line. We want to show that the pink is satisfying the second line.
Yeah. So actually the pink and the white have to both, satisfy this simultaneously.
Right. So
yeah.
If white satisfies the first line, why pink doesn't satisfy the second line?
Yeah, and actually now that I think about it, I think pink does satisfy this.
So this is another example.
Yeah, so remember that red is not an adjunction. Red is
red is
does not satisfy. Yeah. But white and pink, I think, satisfies. So let's think about it. 4 is, in this case, the R of D. Everything is mapped on the D side to 4. So we can already say that f of C is less than or equal to D, meaning C must be less than or equal to 4. Well, we know right away that everything is less than or equal to 4 because 4 is the highest thing here. Exactly. So this is the right hand side is always true. Yeah. But if things are less than or equal to 4, does that mean they would be less than or equal to D, their starting point?
They have to, right?
Yeah.
Because white is left adjoint.
Yes. No, yeah. Well, also because D is also the highest element.
Yeah, I don't think that, it's not the left and the right adjoint we're talking about. We're just talking about the right adjoint. The left adjoint would be.
Yeah, this is also true.
Yeah.
So in this case, the white and the pink are adjoints.
Mm-hmm.
And another thing is.
But the pink is a right adjoint, right?
Yeah, pink is a right. Yeah, could it be low? Sometimes you can have both right and left adjoints, I think.
Yeah, but it's not that one is a mapping from one side and the left is a mapping from the other. Left and right are two ways of mapping the right side back to the left side.
Yeah.
Right, that preserves different things. Like this is not a left adjoint because it preserves only envelopes.
Well, actually, it preserves envelope and meets, I think, because trivially,
yeah, you're right.
4 conjoined with itself
Yeah, you're
is
right.
still 4, right?
Yeah, but that's not necessary for all right adjoints to also preserve that. Right, I mean, just from your formula there, if you could go back to the other screen.
Mm-hmm.
Right, left adjoints are not just the F and the right adjoints are the R. Left adjoints are a different function related to F, right? So both of them are coming from D to C. But
yes, that's right.
They are preserving different things. They might both, you might have both, but you separated the two. They're not necessarily the same.
Mm-hmm. Yeah,
yeah,
in
but
this case,
I
think in this case, this one might just be a right adjoint. Another thing is,
can you go back to the screen?
Yeah, sure.
So right adjoint. So we talked about the R. So it's a right adjoint.
Yeah, it satisfies this one. Now, well, we can ask the question: does it also satisfy this? Because it is possible that a
can you write the other one too?
Yeah, let's write it.
Yeah, we can just write it. Just invert it. Yeah.
How does it do this? Yeah, it doesn't like this. Oh, great. This one works. Okay. You guys see this one? Okay, let me just write it this way. So
is F left adjoint?
yeah, so in this case, well, we're still talking about the pink one, right? So the pink one is L in this case, right?
Mm-hmm.
And it maps everything to 4. So this part is satisfied just because 4 is always the greatest element here, right? So this one's fine on the left here. Now, whenever this is true, this must also be true. So f of c must be less than or equal to d, which means everything here must be less than or equal to the starting points.
It satisfies. Right?
No. So now I'm seeing the problem with what we're saying, because let's think about this case here, C. C here is not related to B, right?
Mm-hmm.
But B is less than or equal to, so 4 is less than or equal to itself. So B is mapped to 4. 4 is less than or equal to itself, but B is not related to C.
Okay. But not related means what? I mean, it doesn't mean that it's lesser or...
Yeah, less than equal does not hold.
Yeah. Okay, but...
And then, yeah, what did we do previously? Here. And then these two go here. And then we're saying everything here gets mapped to 4. So we'll just say here, like,
so let's see if the left side satisfies the left adjoint. The left side says C less than or equal of L of D. So you need to first draw L of D to make sure that, yeah, right. Write the second part too.
Okay.
So we know
L
the
of
right side is already satisfied with white.
Yeah, but the thing is, they need to be tied together. So we need to choose.
No, I know, but I just want to make sure that I just wanted to make sure that the right side. So what I'm saying is this side is correct because this has to do with the white arrows. F of C are always less than D.
Yeah.
Right. So this side is okay.
Mm-hmm.
So the pink has to do with this side now. We need to show that this side is okay.
Yeah, so if we take this side in isolation, it's also okay because everything gets mapped to 4, so everything's going to be less than 4, right? We know that.
Right.
Because L of D will always be 4.
Right.
Yeah.
So, but that actually, originally I thought, oh, that's enough. We've proven the left and we've proven the right. Therefore, we should be fine, right? However,
we need to make sure that they are right simultaneously.
Simultaneously, yes, exactly. That's where we haven't actually checked all the cases because, for example, B is not less than or equal to C, right?
Yep.
So in that case, if something is mapped, actually nothing gets mapped to C anyway, right? By F.
Yeah. And nothing gets mapped to 2 or 3.
Yeah, let's just think of this case. So 2 gets mapped to B, 3 gets mapped to D, and 4 gets mapped to D. And in this case, F of C becomes B, 2 becomes B, 3 becomes D, and then 4 becomes D. Right? So this is our choice of C. And then L of D. So in the case of all of them, they get mapped to 4.
Mm-hmm.
So now we check whenever C is less than or equal to L of D. So that would be all 4 of these, right?
Mm-hmm.
F of C must be less than or equal to D.
Yeah, that checks as well.
But what's our choice of D here?
It's the same. It's always the same D as the D as taking LD, right? So.
Yeah, no, but the problem is that the L of D here, we haven't specified what D is. We just know by the definition of L that everything gets mapped to 4, but we didn't choose a D here.
Yeah.
Yeah, I guess my confusion right now is
yeah,
when we choose a D.
It would have been better if you used X and Y. See, so X less than or equal L of Y, and F of X less than or equal to Y. So then in that case, we don't confuse
so saying,
D.
Yeah, that would make it better. So you're saying this, right? So X is less than or equal to L of Y.
Yeah, the variable name and constant name is the same. That's why it's confusing.
Yeah, this is confusing. Yeah, I don't want to lose too much time on it, but let's try to figure out.
If you just write D after C here, if you just write all the options for C, for D here, right?
So the first part for any x, we know, so like you said, that both sides of the equivalence is true. We just want to make sure that this is true simultaneously. Mm-hmm. So if you take any of these variables, or sorry, constants, and put that there. So for
but if you just write it like this, x and y, then ly and f of x, like this.
Yeah.
And just write the list here, right?
Yeah.
1, 2, 3, 4, A, B, C, D. This is always 4, right? All A, B, C, D always map to 4.
Yeah.
And this here, f of x, is either B or D, right?
So B, B, D, D.
Yeah, so just choose a case and check.
Yeah, but how many times are you checking? You're only checking 4 times? I'm saying you need to check 8 times. So it's actually 2 different tables. One starting with Y and one starting with X. This column here is not like really being checked, right?
But in this case,
or is it? I don't know.
Yeah, it is. Because it's all.
Oh, you're right. You're right. I mean, you have to check 8 times, but no matter we check 4 times or 8 times, the values don't change, right? The values, all possible values are in this table, but you have to check it 8 times.
Right. Yeah, I see you're right. Yeah. Okay, so for now, let's say it is an adjoint. We'll have to, after the meeting, I'm gonna look at it again. So one thing I know to be true about it is adjoints are unique. So if this is an adjoint, there's no other adjoints. There's no other right adjoint, right?
Mm-hmm.
If we're saying that, and so are we saying this is both right and a left or just right?
No, both.
Both, right? Okay.
Yeah.
So that's it's unique. It's both a right and a left to F.
Right.
Okay, and it's not inverse. So this is the kind of the nuances here of choosing adjoints. They're not necessarily only left or only right. They can be both, and they can also be non-inverted.
Mm-hmm.
So here's an example of one that is an adjoint. I didn't check if it was left or right. I think it's right, specifically only.
Yeah.
And in this case, visually, you can see what's going on as and this is covered really well in the 7 Sketches book, but the red arrows are always beneath the purple arrows. You never get a case where a red arrow crosses the purple, right?
Yeah.
This is what I mean by going back along the arrow. So like this purple arrow, you follow it backwards to D, and it must be the target of all the red arrows should be
below it.
Below it, yeah.
I mean, that's why I said that it seems to me like if monotonicity is like you have some stuff here with some order inside of it, right? We don't know. We don't need to know what it is, but we know that when it moves here, this other stuff preserves some of it. Like so, here stuff was growing so between the lowest and the most enveloping term, right? And we know it's monotonic because something of this structure is also preserved here, right?
Mm-hmm.
So we're not then comparing the original set with this new one. We're comparing this map back to this one, right? Like we just want to make sure that, let's say, this connection, for example, when I go back with some other mapping. It might actually not map back to this. It maps to something like slightly less curved,
yeah.
right?
Yeah.
But if this mapping carries some information that is similar to this other one, which is nonetheless still not totally a return, right? They still can be adjoints, right? So it's like a weaker version of this inverted correlation. So in the end, you'd say, it's not really about matching this set back to this set, but matching this arrow with this arrow.
Yeah, those arrows,
they are about the information of the arrows, not of the sets, right?
Yeah.
That's
so
what's
let me
weird about it.
Yeah, it's weird about it, and also I realize now that this can't be, or not that it can't be, but I don't think this is an adjoint proper, this pink one, because if it were, then we could say trivially that any map, the arrow going all the way to the top would be an adjoint. But this contradicts what I was saying earlier about adjoints being unique.
Yeah, it's true. A map that
So we made the statement just now that a map that takes everything to the topmost element must be an adjoint.
Yeah.
Right? But then in this case, we would have two adjoints, two right adjoints. This purple one that I'm showing here and the one that goes all the way to C. And I'm saying that there's an extra constraint. Yeah, it wouldn't be unique. And I think what we're missing is that we're also bounded, not only lower bound, but also the upper bound, because these purple arrows cannot go up above another red arrow as well. Just as these red arrows cannot cross the purple arrows cannot cross the red arrows. So if we had a
this
map,
is what last time you described, that it's really the difficult intuition for me, like in this and in this, you're not relating like in the inverse, where you're really like, if C is smaller than D, then F of C is smaller than F of D. It's not like the relation inside the codomain keeps the information in the domain, right? It's a weird mix of the two in both cases, right?
Yeah.
So it makes sense that it's actually a way of describing a constraint that of the mappings, not like just mapping on the set like we were trying to check, right?
Yeah. Exactly. Yeah. We were making the mistake of trying to check left versus right, like,
and not left
in
functions and right functions.
Yeah, we weren't checking left and right function, and that's the tricky thing. I'm pretty sure the 7 sketches gives you a good way to check it, but it's not like this table that we drew. I mean, it's some other kind of table, I think. But I give you another example that was much clearer to me from I think it was John Baez's online course, which is this example of the natural numbers and the function f of x equals 2x, right? This is obviously monotonic because it maps everything to in an increasing way, right? Right. So the order is preserved. 1 is less than or equal to 2. 2 is less than or equal to 4. Right. This is, in this case, this is the white arrows. Okay. However, if we're talking about the natural numbers, meaning no fractions, right? There is no strict inverse to this function, right? Because normally we would say, oh, okay, then f inverse, it must be equal to 1/2 x, right? But the problem is, like the number 3 wouldn't have a target because 1.5 or 1 1/2 is not allowed in the naturals, right? So this is not allowed. Yeah. So the natural or the correct adjoints here would be so the left adjoint would be this and the right adjoint. Maybe reversing this, but yeah, I think I might be flipping this around. So check the book afterwards, but I think the right adjoint is this one. The left adjoint is this one. So what does this symbol mean? Oh, it's the rounding of this. So in this case, 3/2 gives us 1.5, right? Right. This will always get rounded down. It's the floor operator. So this becomes 1. And in this case, it gets rounded up.
Yeah, I think it's the opposite, right? The right adjoint, I think it preserves meets. Mm-hmm. No, sorry, joints. Sorry, joints are the envelope, right?
Yeah, right adjoints preserve meets.
Meets. So it rounds up, right? It takes 2 and refers back to the above one.
Is that true? Okay. Yeah, I always forget which one.
Yeah, there are too many names for conjunction, envelopes, meet, joints.
Yeah, it's really
upper.
Headache.
Yeah.
Okay, but you guys understand the idea, though. Yeah, it might be right that L and R are flipped here.
Yeah, but it doesn't matter. It doesn't matter.
Yeah, it doesn't matter. Yeah, but you see how like L and R here are kind of fixed by F, by your choice of F. Like I choose f of x as 2x. I only get these two, and they're determined by my choice of F.
Mm-hmm.
Yeah. Right adjoint is join, and left adjoint is meet.
No, I think right adjoints preserve meets, and left adjoints preserve joins.
Mm-hmm.
In this case, it doesn't really make sense with the natural numbers because there's no.
So then floor and ceiling is correct.
Yeah.
So right adjoint preserves by using floor operator because that's the meet.
Mm-hmm.
And left adjoint preserves at ceiling, which is the join.
Yeah, why does it preserve the ceiling?
Well, you wrote that, right? So you're saying here
mm-hmm.
that left adjoint is basically taking the value and take the ceiling of that value. Well, to me, that means join, no?
Yeah, but preserving actually means, that's interesting. It might be the opposite here.
Yeah, but I think that it's already, I mean, enough to realize that, you mapped whole numbers to pair, only even numbers, right? That leaves out all the odd numbers in that codomain that which you map, right? And then you need to decide if, when you map, let's say this codomain back, if you bundle the odd numbers with their upper even number or with the bottom one, right?
Yes.
In both cases, something is preserved because again, you're not getting the inverse, right? But you're still preserving something about the codomain that you're mapping back. And I don't know, exactly. I think just so we can move, because I know you have a lot of stuff also to talk about, but just
we shouldn't get stuck.
Yeah, I mean, this is the problem with this. Like, everything is like a dense fat, right? Everything you can go down into it like forever. And but I think that this idea that it's for me, it's very clear from your examples that this is a very strange kind of splitting of the concept of mapping and inverse mapping, because suddenly you get you get a sense of comparing if the mapping from a domain to a codomain is not similar to the domain, but how similar it is to the mapping itself, right? You can say, yeah, it's not really matching, but it's still preserving some information, right? So, like I'm not sure if this is a good example, like if you have a recipe with 10 steps, but you're kind of a lazy cook, so rather than taking 10 steps, you like take 5 in that recipe, and you kind of skip some stuff, make some stuff slightly different. Still, it's monotonic because the basic order of the steps was preserved, even though it took less steps, right? But now if I look at what you did and I try to reconstruct the recipe, it won't give me the original recipe back. But that mapping onto the recipe space, right, into like a program, it will have some relation with the move from the recipe to how I did it, right?
Yeah.
So
yeah, because we have a constraint.
I understand what Gabriel is talking about. It's like you are allowed to collapse some steps, like, but the order is preserved. So the issue is, when does one divides into 2 or 3, but the order nevertheless is preserved because you don't have to, you don't get to cross any lines.
Mm-hmm.
So
yeah,
something like that in a sense, right?
You know what? How
exactly.
I think this is a good example for this. Like for example, you have music. Like for example, you have a music sheet, and you play the music. Like you're not following the rules, but basically something is preserved of the information that was in the music sheet. But now if somebody notes down the sheet for the stuff that you played, right?
Yeah,
I mean,
like when you play music, for instance, you are always kind of how do you say that? Kind of how do you say arredondar?
Rounding up, yeah.
Rounding up things in a sense, right? So when this is a good example. So you read from the sheet, you get some information translated, and then you get somebody to not to consult the original sheet, not shit.
Depends on if I'm playing.
Maybe if you're playing is shit, not
yeah, exactly.
music properly, and you're shit. So maybe the sheet music that will result from this is kind of different. But in a sense, there will be kind of if you're not completely awful, there will be a kind of order preserved in a sense. Like you don't have all the information from the original sheet. Maybe you have even more information. This is unclear, but nevertheless, there is some kind of thing that is ordered algorithm going on.
Mm-hmm.
That you can map, maybe not one by one, but 1 to 2, or 2 to 1, or 3 to 1, or 1 to 3, and then something like that, right? But you don't get to cross. Like it's not like I will play a section of the song in a different order. No, this will be preserved, right? So some details get lost, but nevertheless there is an order. There is a preservation of the order, right? In a sense, the recipe is the same. Like you have to make a reduction of butter and wine, and instead of doing this, I'll just buy something at the grocery store and use it. But nevertheless, you are doing the basis of your risotto or something like that, but in inferior steps, something like that, right? So it has something to do with collapsing something. But
yeah, what I think the difficult intuition, which I think is the thing Dennis said for last, is that okay, this gives you an idea that you can compare mappings and not sets, because you're not really interested in exactly like comparing the exact song with their. So you're comparing how one thing was interpreted one way or the other. But what makes this hard is that if there is a joints in this formal sense, they are unique, and this is not valid for what we're saying, right? I mean, recipe thing is not.
It would be right, exactly. So in the case of transcribing music, that's one arrow back, right? But then the other arrow the reverse or the inverse arrow would have to be someone playing the music from the transcribed sheet music.
Yeah.
Right. But the key is that the way you transcribed it must determine how they play it in an exact way. So because if we say transcribing is F and playing is R, let's say it's a right adjoint, then for any transcription, there must be exactly one way to play it.
Mm-hmm.
But in a way that is based on what information was lost. So in this case, like one maps to 2, 2 maps to 4.
Yeah.
There's no place for 3 going back. So now 3 has to choose. I either go back to 1, which means 6 goes to 2.
Right? I think that translates like this.
Or 5 goes to 2.
If you play a music wrong, like if you simplify a song when you play it, there's still only one transcription of that kind of terrible playing you just did.
Yeah.
You see my point? Like it does preserve uniqueness because it's not uniqueness of all possible transcriptions back. It's the uniqueness of that transcription. No, I think it makes sense.
Yeah, it would be like if I transcribed it and I left every other note out or something. Like I left out some key information from the transcription. And then
I do that all the time when I cannot play like some crazy virtuous thing in a sheet. I like just kind of play something in that scale, you know, like it does respect it somehow, but
exactly.
And the opposite is true as well. Like it's very common to have like sheet music that is kind of a simplified form of what ought to be heard. So in jazz music, this is always the case, almost. You have in jazz, you have like this very simplified form of the theme, but the guys are doing all kinds of, you know, anticipations and retardations that are not exactly what's going on there. So the point is, in a sense, to have the order preserved, but not the time points exactly preserved. The right time points, so to speak. Something like that, right?
Exactly, yeah.
But it's cool. I mean, I mentioned this example of music sheets and things like this because you can see that adjoints and the whole discussion on morphisms in categories, it does give you more vocabulary to talk about, you know, the relation between music playing and music sheets and notation, right? Because suddenly it's not about is it the notation or not, right? You can
it's more subtle. Like you know, classical, just a brief comment, the classical, I mean, analytic way of doing this, you know, Nelson Goodman's chapter 4 of Languages of Thought, wherein he offers what he calls perfect compliance, which is actually a bijective account. So you have one thing, one note and one sound, one note and one sound. If you don't, if that condition is not satisfied, he's worried that you get a sliding of identity. So if you change one note, you can change every note. This is very, very strict. This is why he's very strict on the logical conditions for this to obtain, right? And this is more interesting because it kind of relaxes some of his conditions, while at the same time does not lapse back into, you know, anything goes.
Exactly. Yes, that's the key I'm trying to capture. That okay. So as a side note, yes, it's correct that this is the left adjoint from the 7 sketches, right? The ceiling. The ceiling is the left adjoint. Okay, and then the other thing is exactly. So we are constrained by the top and bottom red arrow here, so that this purple arrow cannot really pass. So we can't map all of this stuff back to the top of C because that would be crossing some stuff, right? So there's some constraint that limits the space of choices here to exactly one thing, but it's still a relaxed version of an inverse.
So the example we had on journal, was it a correct example?
No, this one's incorrect. This is not a, so when we said this, right? This is neither right or left adjoint to F because it crosses these white lines, right?
It does, but why crossing is a no-no?
Because it's not preserving the functions. It's not about preserving the order in the set. It's about preserving the order preserved in the function.
Okay, but where is it said in this equivalence? What you just said.
Yeah.
How do I?
Yeah, how do we parse it into this?
Yeah, it's written here because it's not relating sets. It's relating relations between sets. Like it's something in the domain with something. I mean,
yeah,
I think,
but nevertheless, you can still choose the points here so that we can break this.
No, but I think that's what I got wrong at the first time. Like, isn't it in fact that this and this are both here?
No. Oh yeah, you're right. Yes, L of Y is on the left. Yeah.
No. Yeah, exactly. So you're talking
yeah.
about, sorry, you're talking about something in X and something that came from Y.
Exactly.
So, but this is the crucial part, right? So you're comparing
you're comparing an element in X to the target of an arrow coming from Y.
Yeah, and yeah, I think
which is also an element in X, but yeah.
Yeah, but I think
I just want to choose some ones so we can see if we see the problem, right? If X is 2 and Y is B. No, sorry, let's say Y is C. Okay, so is X less than or equal to L of C?
Which it is.
Yes, it's 2 less than or equal to 4, basically, right? Yes. Now, is F of X B less than or equal to 2? Or sorry, C. Right?
F of
no, it's not.
F of X, which is 2.
Yeah, F of 2 is equal to B, which is not less than or equal to C. Sorry, my mouse is breaking here, but this is not true. Why? Because B is not related to C. B and C are like not on the same chain.
And is this because the lines are crossing?
In this case, it's because actually 2 map to B, which is unrelated to C.
Right.
So okay, so there's a relation here, right? 2 is less than the 4, but B is not less than to C.
No, I get that, but my question was, how do we? You said that the lines shouldn't cross, and I was asking how can you parse that into this equivalence?
Yeah, so that is true that this is crossing here, right? Yeah, I'll put it this way. Because 2 is less than 4 here, anything that 2 gets mapped to must choose to get mapped to either 2 or 4. And then same thing for B and C. Anything, B and C are not related, therefore they can't be mapped to the same thing. Let's put it this way. It takes 2 trips to verify this rule. You have to take C, following the pink line, to 4, and then back again, you get D. But this is not less than or equal to 2 mapped to B going back to 4.
Yeah, so you have to take 2 paths, and those paths should not cross. That's what you're saying?
Yeah. I'm saying that the path you took with
so
the
for
pink
any
line,
point that we choose, in order for something to be right and left equivalent, the paths that you take cannot cross for any point.
Yes. But this is not a rigorous proof of it, because I mean the rigorous proof is this, right? If you find some case where this doesn't hold, then it's not true. But yeah, the question is, okay, can we, just by looking at this, the white arrows, the F, could we tell that it doesn't have an adjoint? And I don't know how to do that. I don't know if there's a easy heuristic we can use to determine that without checking every case, right? I do know, yeah, lines crossing is already a non-starter, yeah, no. And I think I have a hunch now that when 2 elements are not related, that can also be a non-starter, because B and C are not related, but yet I'm mapping C to something that is related to 2. Namely, 2 is less than or equal to 4. So 2 is related to 4, but B is not related to C. So those 2 things can't map to each other, because relations have to be somehow preserved.
So what if we mapped B to 2 and C to 3?
B to 2 and C to 3.
That doesn't seem to cross.
Yes. B to 2 and C to 3. I think that would be okay, yeah. That might be an adjoint. Now, but what about A, though?
Yeah, in that case, A has to go back to 1, which is the case of 1-to-1.
Yeah, no, this wouldn't work because 1 is less than 4. 1 gets mapped to B, which is greater than A. Yeah, it might be left, but not right adjoint, one of those. Oh, no, this wouldn't work at all, because if B mapped to 2 and C mapped to 3 and A mapped to 4, then that would be breaking monotonicity, right? Because A can't be mapped to anything greater than what B and C are mapped to, right? So yeah.
Correct. So in that case, A has to be mapped to 1, which is the trivial case.
Which is the trivial case, exactly. So the only adjoint here is the trivial case, which is the inverse monotonic function. Okay. But let's, yeah, I don't want to, we've already spent half the meeting, I think, on this, so. And there's one more slide on it as well. So the original idea for this came from Galois, and it's called the Galois connection.
What's the name of a possible movie? The Galois Connection.
Exactly, it would be an amazing movie. Anything about
Galois.
But in its original form, it wasn't actually a monotonic thing. It was a antitonic, meaning order reversing. So actually, that the right-hand side of this formula was a greater than. So C is less than or equal to L of D if and only if F of C is greater than or equal to D. So it flipped the order. And that's still considered a Galois connection, but and it's the original one. but today people use monotone more often. And just as a historical note, this is the fundamental, or has to do with the fundamental theorem of Galois, which was used to show, the famous, there are no real solutions to the quintic. Is it, I think, quintic form, like quadratic equations, and so on, right?
I think it's quintic, yeah.
Yeah, quintic equations or greater. You can't find like rational or real solutions. They must be done on the complex plane and so on. And it has to do with exactly this correspondence. In this case, it's between fields and groups. So of course, I cannot go through this, and we don't have enough time anyway. But yeah, it's something nice to think about. Like the origin of this is very interesting. Okay, so that's actually a review of what we talked about last time, was relations and posets. And now we understand adjunction a little better. So we can move to topologies. So I added a note here, which, yeah, actually it's not that important, but it has to do with reflecting and preserving functions. So we say that something preserves a property when that property holds in this way. Like if a property holds for a C object, then it holds for the image of a function, then we say F preserved that property. But we say that F reflects the property when we flip the direction. We flip the two terms here, and we say, oh, if it's in the image, then it must have been in the source. Okay, and so a function that reflects open sets is called continuous. Yeah, and then we talked about manifolds. I think we mentioned local versus global themes. Actually, I wanted to show you guys this nice app here. You guys see this?
Yeah.
So this is a quotient space where it's glued in the same way that a 3 torus, so like a 3D torus or whatever, is glued. Right? We looked at the case of a 2 torus, but if we wanted to glue like a 3-dimensional space, the way a torus is glued together, it would look like this. Yeah, just to give you a sense of what is shown here, but in 3 dimensions, right? So if you're on the surface of this sphere, you will your field of vision is described by these green lines. So what you will see is the point opposite to you, in all directions. And then beyond that, you would see yourself. And then beyond that, you would see, again, the point opposite to you, and it would just alternate, right? So that's kind of what this is showing you, right? So this is how, like, okay, the global thing is not seen, right? The global thing is inferred from or one can be inferred from the other. It's actually a bit like bracketing, right? You can see the global here, but you can't see the local. Or you can see local, but you won't be able to see the global, right? And the relationship between the two can only be described by something like a morphism. And these are actually called sections, right? So the total space would be the map from the tangent space to the base space, which is in this case a manifold. And each one of these Euclidean looking surfaces, these gray surfaces, are called sections of the map. So here, so if you have some very complicated space here, and you have like a simpler space, let's say a sphere here, for any morphism F, we can find small patches of where F landed and see what it looks like in the original space. So this is called F minus, but restricted to these small, this small chunk of it. Does this make sense?
It made sense, except can you flip back? So this local versus global thing can be characterized as a morphism from a space called the tangent space to the manifold. Mm-hmm. So tangent space is that U?
Tangent space is this more complicated space here.
Okay.
Yeah.
And the manifold in this case is here.
Yeah, this is the manifold, or we call it the base space. So yeah, in this example, it's a manifold, but in general, it can be any kind of space, right? We just call it the base space.
Okay.
And then here, in a normal case, or in general, it can be any kind of space, but in here, it is the tangent space, right?
Okay. So now, can you flip back again?
Okay.
So the local versus global thing can be characterized as a morphism from a space called the tangent space to the manifold. Locality in this case is then described by the pointwise sections of this map. Okay. Yeah. So those pointwise sections are like U's.
Exactly. U is the local. When we say local, we mean this section here, this right. red area. So locally, this looks Euclidean, maybe, or has certain properties. Right? Globally, it's not. It can be something else.
Right.
Yeah. And then we describe it in terms of morphisms as the inverse restricted to a subset, right? So normally we have a function f. It maps everything here, right? But if we want to restrict it, we can say, we can pick out some area here, call it U, and write f of U here. That's a smaller chunk of f. So that's exactly what's happening here, right? F, in this case, we're looking at the inverse of f, and we're choosing, so the inverse of f itself is like everything, right? This entire thing is in f inverse. Mm-hmm. Mm-hmm. Yeah. Okay, and then I think we haven't talked about algebras, but I think we can skip algebra and logic because it's something we've already talked about many times. Just the closure of algebras is important, right? So whenever you have an algebra, if you combine elements in it, you stay within that algebra. And that property is called closure. And then we have Boolean algebras, hiding algebras, which we talked about a lot. For hiding algebras, what's important is you not only can you take values besides true and false, but also you have this notion of a pseudo complement. So because in Boolean land, if you take the complement of something and you take the complement of that thing, so double complement, you always get your original element, right? A pseudo complement just means it's a complement that if you complement it again, it would not return you back to the original. Okay, so it's a relaxation of that condition.
Mm-hmm.
Okay, so now we can get to categories, which I wanted to spend the most time on. But I think it really depends on, because it's such a vast amount of information and formalism that we probably won't be able to like dive very deep into it, but it depends on what you guys are interested in discussing. So let's define it at least. So a category is a collection of objects, and for any two objects, we have this thing. Let's call it a set for now. Doesn't have to be a set, but in this case, it gives us the collection of morphisms between A and B. Okay. So before I said that between any two sets, right, S and T, the number of morphisms we have in the category of sets is T to the S power, right? So if T was equal to 2, it would be like 2 to the S. That would be the power set, right? So that's how many morphisms exist between S and T. So in some sense, that's how much information is in that space of transformations. So this HOM A of B, in this case HOM S of T, is basically a set of all these functions, right? And then we can do composition. So we've already been using this in our example. So F follows G follows H, and it obeys associativity in this way. And then the final condition is that the HOM of A and A, meaning the morphisms between A and itself, must contain at least one morphism, which is the identity, right? So typically it's written like this. If this is A, this is identity on A. Yeah, and then, with that, you basically get, right? Okay. Then we have functors between categories, which map objects to objects and arrows to arrows such that they respect composition. So in this case, when we say
can you change the color to like white, just because the red is hard to read?
Yeah, it's a good idea. So in a lot of ways, a category is just like a graph, but it's completed so that if I have some path like this, then automatically I get this, right? So when we say that a functor preserves composition, in the formulaic way, this is what it means. If f of a composed pair of arrows is equivalent to the composition of the individual arrows, right? In this case, G and H are arrows. So if this is G and this is H, then I have to make sure that this gets these objects must be mapped in such a way that they preserve this relationship. So let's say this is one category, and then I have another category that is like this, right? So what I cannot do is I cannot map like this, right? Because in that sense, I'm kind of tearing this composition. what I am allowed to do is map everything to here. And this is very similar to what we were talking about with monotonic and collapsing, right? In this case, collapsing is okay because when I collapse everything to one object, the identity, that means like I'm sending G to the identity and I'm sending H to the identity. And we know that the identity composed with the identity is again the identity, right? So in that sense, G, H, and this composed arrow are all going to the identity. So in that sense, we're preserving, in a trivial sense, the composition. Okay, so the yellow here is not allowed. This orange is allowed, but it's a trivial case.
Dennis, go back to your slide.
Yeah.
So let me see if I can read this. A functor between two categories maps objects to objects and arrows. Okay, so first of all, you're dealing with two categories. So white and yellow were two different categories. And so white dots and arrows, you should have used another color for your functor, not yellow.
Yeah, yellow is the functor and the
and the other category.
And the other category, yeah.
Okay. So now go back. So you're saying that if there is a functor that maps a category to another category, that maps objects to objects and arrows to arrows between the two categories, then the functor should preserve these two properties.
Yes.
That if there is a GOH in one category, the functor that maps that GOH also the result is when the composition of when you map G and when you map H.
Exactly.
Okay. Or any commuting arrows G and H for any commuting.
Yeah. So commuting means that the codomain of G is the domain of H, right?
Right.
Or maybe vice versa. The codomain of H is the domain of G, right?
Domain of G, exactly.
Yeah.
Okay, I got you. So in this case, let's see why orange is not, sorry, why yellow is not a functor. Because we are using HOG.
Yeah, so HOG doesn't exist here.
Correct.
Yeah, because we have some functor, let's call it G star. Oh, let me use yellow just to be consistent. G star here, and then we have one H star here.
Yeah, these are arrows. These are
arrows in the target category.
Right.
Yeah. So G goes to G star, H goes to H star.
And there is no GOH in this case.
There's no, yeah, exactly. There's no GOH, so I didn't preserve composition.
Correct.
Yeah.
What are all the IDs? Also, another problem is that not all other identity arrows are preserved, because identity arrow for this is not preserved. Let me get annotation here. Identity arrow for this is not preserved because it's not mapped to anything.
Yeah, that's true. In this case, I can map it to anything else. Yeah, I can map it here.
Yeah, I'm just saying in that example. I just wanted to understand the conditions.
Yeah, no, I forgot to map this one. But yeah, in that sense, this one can go to any of the objects.
Okay.
Yeah, so again, we had before a monotonic, this idea of monotonic property, it was being preserved. You can think of this as just another property, but it's more slightly more complicated because it's because of composition, and actually not that much more complicated, because monotonicity, because it is transitive, is essentially like composition, right? Composition is also transitive in a way. It's like the transitive condition here, but yeah, anyway, so it's preserving some property. And we covered the constant functor, right? So the constant functor is a functor which takes a category to a single object. In this case, this top yellow object. Okay, so now some more technical stuff. When a category is locally small, that means HOM of A comma B is always a set for any two objects you choose, right? Then we can do this thing where we free the second variable of our HOM. So HOM is actually a function, or it's a functor actually. And we can free up the second parameter in HOM to turn this into a functor. And then we can free up also the first term as well. So when I say free up, I mean we can choose any other object, but we keep this A fixed, right? So very simply put, like if I have a function fxy, if I fix x, that means x becomes like a specific term, then I can write it this way, and it becomes essentially equivalent to g like this.
Mm-hmm.
Right? It's like I made a new function. So actually HOM, when both of the terms are free, it's called a bifunctor. It actually takes two categories to one. Right? We don't need to cover that that case. We just need to know this, that a representable functor is any functor which is isomorphic to this or this. Okay.
HOM itself, sorry, can I read this? When a category is locally small, HOM itself yields functors to the category of sets. I don't get that part. What is how to the category of sets? I guess I don't understand the category of sets.
Okay. Yes, I glossed over that. So the category of sets is just the collection of sets and functions between them. So let's say this is a set. And this is also a set, right? And then we have functions between them. Right.
I think that the point is that, from what I understand, is that this HOM, meaning this, let's say, this collection of functions between two objects, nothing guarantees that you can, let's say, picture it as functions between sets. It can be much more general than that, right? So there is an actual restriction so that the HOM of A, B actually is, let's say, like the function between sets, and that's when there is locally small. Is that it?
It's locally small when HOM of AB is a set. So HOM is a functor. It takes, well, HOM with a fixed A is a functor that takes any object to the set of arrows going into or out of that object.
But when you were defining HOM, you said HOM is basically a set of functions between two objects, set of arrows between two objects.
Yes.
Right?
When when I fix the, so let me redraw it here. So this is A, this is an object in a category. This is B.
B. And there are a bunch of arrows between them.
Yeah, there's a bunch. Yeah.
So
A, B. is the set of all these arrows.
So is equal to curly bracket. Let's call this F. Let's call this arrow F.
Okay. Then we say F belongs to.
F belongs to that. Okay. Very good.
Yeah. When it's so that by convention, if I don't label it, we're probably just talking about the collection of all the arrows. Okay. Like, there could be many arrows there. If I say F, I mean like this is some unique or some specific arrow.
Hom is always a set. Now go back to your slide.
Hom is always a set when it's locally small, when a category is considered locally small, which is actually most cases that we care about.
So is there an example that Hom is not a set?
Yeah, so it would be a class. If it's not a set, then it must be a proper class. So that would be something too big to be a set. I don't actually know an example. I guess it would be like something like a V.
I mean, for example, all the arrows from an infinite situation to its power set.
Well, does the size matter? I mean, the difference between set and class is that in class you don't have the axiom of foundation. So self-belonging is allowed in class. Doesn't matter the size, what the size is.
Yeah, but size is connected to that. I mean.
Yeah, not so locally small category. Yeah. I'm sure there's an example here. Let's see. Yeah, I mean, I think this is something we don't need to really know.
Okay.
We can look this up.
Let's move on.
Yeah.
Just wanted to understand the terms. So
no, I think that, I mean, I agree class is not a definition, it's not based on big sets, but I think that since the Grothendieck universe is also a universe where all power sets of sets exist, right?
Yeah, all power sets exist in Grothendieck.
That's too big to be that is a class. I think that's not that set is not, that collection is not a set. I didn't go into it there.
Yeah, it talks about a ZF with a Grothendieck universe U. Small category is one whose objects and morphisms belong to you. A large category means a category whose objects and morphisms are still sets, but not necessarily belonging to you. So it's relative to some chosen you. Yeah. But in general, in ZF, basically anything you can form, a collection of things you can form that don't obey the axioms of Zermelo-Fraenkel, we call them proper classes, right? Which sets are the collections that do obey Zermelo-Fraenkel. So yes, you could include self-belonging stuff, but you can also include other stuff. Anything that doesn't obey the axioms is a class.
Right. Okay. So let's go back to your slide. There was still something that so I'm trying to understand this paragraph. When a category is locally small, Hom itself yields functors to the category of sets. Okay. 2 for each object A in the category. Yields functors to the category. Yeah. So one is Hom A to something, and one is Hom something to A.
Exactly. Yeah.
A representative functor is any functor which is isomorphic to either of these two. Okay.
So let's an easy way to think about this is if I choose some object A in my category, I have a bunch of arrows going out to other objects, right?
Bunch coming in.
And a bunch coming in. Okay. So hom of A dash takes me to the set of all the white arrows.
Yep.
All arrows going out. Going out of A. So which takes A as the domain, right? And then, yeah, then obviously the other one is this case, right? All arrows going in.
So it's really representative of A.
Yeah, you mean like informationally?
Yeah.
Yeah, and then this
you can do this. You can get these two kind of representations if it is a small category.
Yeah. Yes, I don't think I'm not an expert in the, of course, large versus small like categories. I don't know what changes, but I think the important thing is that these functors give us an example of what it means to say something is presentable.
Mm-hmm.
When we say something is presentable in category theory, we mean that we can express it in set theory. So we're saying A, if it's satisfies some conditions, we're saying this is presentable. A is presentable. It gets mapped to, there's an adequate set theoretical notion of A. Right, and we see that this comes in two flavors. The arrows going out of A and the arrows going into A.
Mm-hmm.
Yeah. So we say anything is representable if it's isomorphic to either of these two. So anything that looks like these two, we call it a representable functor. Now, a side note, any category where we flip the arrows, the direction of the arrows, we call it the opposite category. Right, so this is interesting because these are basically the same in the opposite categories for each other, right? If in some category, we call it C, this might be hom A and hom, so hom A dash and hom dash A. But if we were to do the opposite category, then these would just be flipped.
Mm-hmm.
Right? They would send us to, so in this case, like this would send us here and pink would send us up here, right?
Oh. So this is like seeing them in the mirror.
Exactly. Yeah, every category has a mirror image where all the arrows are flipped. And this is referred to as duality. This is very useful because you might want to prove something in one category that's easier, and then you automatically get for free a statement in the opposite category.
Right? Like the frames and locales are.
Exactly. Frames. Yeah. If you prove something for frames, you can probably, with maybe some work, get an equivalent statement in locales.
So remind me, was frame join locale meet?
Frames are preserving joins, I think. Yeah.
Okay.
Frames are upward.
Yeah.
Inclusion. Locales are downward, so restriction.
Mm-hmm. Mm-hmm. And given a category C, does the opposite of C always exist?
Yes, always exists.
Okay, and it's always a category.
Yes.
So if a category, we have a C, then opposite of it satisfies. I mean, what collection of objects and arrows satisfy a category? There has to be a property for the category, right?
Yeah, these two properties here. Composition and identity. Oh, sorry, these are functors. Sorry, these properties here. So it's actually composition, right, which is associative, and then also Hom A of A always contains identity. So there's always an identity.
So opposite of every category meets these conditions.
Yes.
Okay.
And we can see this visually.
Is that an axiom, or is it like something provable?
We can prove it.
We can prove it? Okay.
Yeah. So given any arrows like this, we just form the opposite this way. Right?
Yeah, I mean, opposite of ID is trivial. It's just, yeah.
ID again, yeah. ID again is
but I don't know if the opposite of transitivity is trivial, but I guess, okay. It's trivial in these as trivial examples, but on a general case, I don't know. Okay.
Yeah, I see what you mean though. Like, is it true that these morphisms will be the same as these other morphisms? Not necessarily. Right? There might be.
No, I mean the opposite of these morphisms satisfy transitivity property. In general case, I mean, it makes sense from the pictures you're drawing, but I don't know whether there is a proof for general case.
Yeah, that's a good question. Yeah, maybe we can look for that. I think whenever I look for this type of proof of duality, they give you a really hand-wavy kind of case, like just look at these arrows and then flip them around. You know? It's like it's beneath them at some point to prove things outside of category theory, but yeah, I mean, for sets it makes sense, because for any function you can find a function that reverses it, but not necessarily the inverse, right? Doesn't necessarily have to satisfy the inverse condition. Okay. Some more terminologies. We consider any functor from the opposite category to some category contravariant with respect to C. Okay, so if you see the C op on the domain, we say this is a contravariant functor. If D is the category of sets, then F is called a presheaf. Right, this is the most general notion of presheaf. The original notion had to do with spaces and sets, but this one is just any category, any opposite category sent to the category of sets. Then this is F is a presheaf. Okay, and the dual of that statement, which is we flip C, and we're now saying this is a co-presheaf. So
if you want to sound like a category theorist on Twitter, you just put co in front of everything.
Yeah. Yeah, everything seems harder if someone says co, it like kind of scares people because it's.
Yeah, it's not enough to have homologies. You need to have co-homologies. Not enough to have.
Yeah, co-sheaves.
So there is, I'm slow, so I'm learning this. A functor F C op goes to D. So D is a category, is considered contravariant with respect to C, okay. If D is the category of sets, then F is considered a presheaf, okay. Dually, a functor F from C, not opposite, to set is called covariant, okay. Makes sense, because co is always something has to do with the duality. Okay.
Yes. So yeah, and just to make it clear, presheaves are always contravariant, right? So
yeah.
In this case here, it's C opposite to sets. That's a presheaf.
Yeah, presheaf.
C to sets is co-presheaf. Yeah.
All right. What is this pre for? Like, what's the significance of pre?
Yeah,
like
it's not
sheaf?
yet a sheaf.
Not,
yeah, it's
Still,
relaxed.
yeah, it relaxed on a condition.
Yeah, there's some conditions which we'll get to.
okay.
Okay. And then one more piece of terminology before we get to the fun stuff, right? A pre-sheaf, which is isomorphic to, remember this from last time, right? Hom dash of A.
Mm-hmm.
So for some fixed A is a representable pre-sheaf.
Mm-hmm.
Okay. And again, we have representable co-pre-sheaves, which flip this around. Okay.
Mm-hmm.
Okay, so now that we know what a representable pre-sheaf is, it satisfies all this stuff, and then it also is isomorphic to this thing. We can, we need one more thing, sorry. We need to understand natural transformations.
But how could, sorry, again, can you go back? I'm missing something.
Yeah.
Can you go back to the previous page, functor? Hom, we said, is a set. Pre-sheaf is a functor. How can a functor be isomorphic to a set?
Hom is only a set when you've fixed both A and B, both parameters. But when you, so that's why I said it yields functors. It isn't itself a functor yet. It yields functors when we fix only one of its terms. Right?
But go back to your Blackboard. So in the
Blackboard, yeah.
Yeah. So in this case, the white arrows coming out of A, these white arrows, can you see my mouse?
No, I don't see your mouse.
So these white arrows, can you see it?
Mm-hmm.
So this white arrow, these white arrows.
Oh, now I see it, yeah.
Right. So these white arrows is hom A dash.
Yes.
Right?
Yeah, the collection of all of these.
I missed that part of the definition that these white arrows, which are arrows within category C, is defined as a functor because we are still in category C, whereas you said functor is between two categories.
No, because the arrows are collected in a set. So this is a functor to the category of sets. And actually, you're right. So yeah, this is not a great presentation because I'm assuming here that we're trying to see all of hom A at once. But in reality, it's a function because you're picking every object out from C and forming like this, right? So when we say A is fixed, we mean like all of these are valid sets.
Right.
Right?
Right.
So B, C, D, they're other objects.
Mm-hmm.
So this is captured in the idea that we have one function, or one functor, sorry. Looks like this. It's a functor free in one variable.
So it's a functor between what and what exactly? It's a functor between, so this hom A dash is a functor between which categories? Category C?
And sets.
Oh, I see, okay. Got you.
Yeah, because we have sets of arrows, right?
Okay.
So if I chose B, then I have the set of arrows between A and B. If I chose C, I have the set of arrows between A and C. And those two sets have functions between them as well.
Right. So in this case, these are the set. This is like a codomain of that functor, if there is such a thing.
Exactly. It's the codomain.
Right. Whereas this is, or this represents the functor from A to
C. From C, yeah, from C to set.
Yeah, okay, I got you. Never mind. Okay.
Yeah, exactly. Yeah, no, it is a bit confusing, and especially the first time to see it, it's like not very intuitive. I agree, but I don't know of another way to present.
No, it was really good. So I missed that part. So let's go back to the next page.
Okay.
You're saying a pre-sheaf is isomorphic to HOM dash A for some fixed A is a representable pre-sheaf. Okay, got you.
Mm-hmm. Yeah. So we said here that HOM A dash is C to set, right? Well, we also know that the dual is this. So that's C opposite to set, right?
Mm-hmm.
Yeah, and then we said that any functor that looks like that is considered contravariant, and in this case, if D is the category of sets, then it's a pre-sheaf.
Mm-hmm.
So I would say that pre-sheaf is a specific case. Sorry, not specific. HOM dash A is a specific case of a pre-sheaf. It's a representative pre-sheaf.
Mm-hmm.
So pre-sheafs in general look like this.
Mm-hmm.
HOM dash A is a specific kind, a special kind.
Guys, sorry to interrupt. I'll have to leave now. Something came up here with the building. They're asking us to talk. I'll just leave the recording going on, and I'll see everything afterwards. I just wanted to tell you, Dennis, also, since you're the next presenting, I mean, I don't think it's a problem if you also plan to take a part of the meetings before we get to the book to also continue stuff that you think is worth discussing. You know, like if we take like half an hour before everything to also go through more stuff.
Yeah.
You know, like something like this, if you think it's a good idea.
Yeah, I think we could go through, I mean, there's of course a lot more stuff here. I think understanding just up to the Yoneo lemma and then understanding pretty much the rest of these slides, it should be enough for everything that Badu shows in the book later on.
No, I'm just saying in case, I'll have to go now, but in case, let's say, until
we should stop maybe then, because if Dennis can just finish this in the beginning of the presentation, the relations book, I guess it's okay, right?
Yeah, I'm not saying that he should do it, and I know that it's not that much, but I'm just saying in case you want to do more stuff.
You guys reschedule this for me. I think it's okay if we reschedule this for you because you have to go, right?
No, I don't need to reschedule. I mean, the meeting is already happening. I can just like listen in afterwards. It's like,
yeah, let's just do just the next two slides.
Yeah,
because I think that's good enough for us to continue next time, because then it kind of changes topics after that.
Perfect.
Yeah.
I'll see the end of it then in the video, but I'll just leave the recording going on.
Push yourself,
Okay.
Gabriel. You are not muted. Yep. Great.
Okay. All right, so we understood this part. That is, there's this thing called a representable pre-sheaf, okay? And let's give it some intuition first. So like we said before, we are assigning for every object some set of arrows to that object. So there can be other pre-sheaves that assign other data to every object. Right? So the whole point of the pre-sheaf is it's not just this arrow diagram I showed here. It's just to say for every object in the category, I want to assign some sets to them. Let's use boxes for sets. Right? Such that given a function from one object to another, I get a function between their sets.
Between the sets, okay.
Yeah, that's the key here. That's the intuition, right? But these sets can be arbitrary data. They could be, for example, if the arrows on the left are exchanges between commodities, or like buying and selling things, the things on the right could be like arrows in their price of their prices. Right?
The arrows in the codomain are contravariant to what in relationship to the arrows in the domain, right? Like they are opposite. Yeah. Okay.
They're opposite. Yeah. So it's not clear from this diagram, but yeah, this. If you follow the arrows here, right? These two objects are sent to these two boxes. So in this case, right? And then this white arrow is flipped here. Oh, sorry, here.
So this is like the Galois ordering.
Yeah, the antitone thing.
The antitone.
Yeah, antitone, yeah, it is contravariant. Yeah. Yeah, so monotonic means preserving, right? Monotonic means if A is related to B, then F of A is related to F of B in the same way. But the antitonic would be if A is less than B, then F of A is greater than B, right?
So it's an antitonic relationship right there.
Yeah, this is antitonic, yeah. But they use the term contravariant more generally. It's a generalization of that idea. Yeah, so this idea is very nice because you're basically saying, I have some space of things here, these dots corresponding to regions of space. And this is kind of the original intuition, right? And then I want to assign to this spaces sets. Yeah, red is not a good color. But I want to assign sets such that the set I assign to this one includes the set that's assigned to the one inside.
Mm-hmm.
Right, so I have a notion of restriction here. So just like we had maps between, right, this set to this set.
For instance, if the arrows indicate inclusion, for instance, right?
Yeah, exactly.
Okay.
Yeah, well, yeah, in this case, it would be restriction, the opposite.
Restriction, okay.
You're restricting one set to its subset.
Yeah.
Yeah, and on this side, it would be inclusion. So this inner circle is included in the outer circle. Right?
Yeah, I see.
Yeah, like this. Yeah, so this is where contravariance comes in, and it's a very spatial notion. Okay. So now this part, I'll try my best here to say it. I mean, it's
everybody gets in trouble when trying to present natural transformations. I've seen this presentation a lot, and everybody finds it difficult to make it intuitive, right?
Exactly. Yeah. The intuition. I feel like the intuition kind of stops here most of the time when you encounter categories. It becomes too many levels at once. But let's try anyway. So we know that now how to define functors, right? Functors are things that map categories to other categories, and they preserve composition and identity. So a natural transformation is a map from one functor to another. But the way to think about such a map is by taking the objects and the arrows of one functor into the objects and arrows of another. And so all of that is a way of describing this naturality square. Okay, so before, sorry, did you say something?
Sorry, no, I
okay.
was talking to somebody else. Sorry for interrupting.
Oh, no problem. So let's say you have a category C here, and it has some stuff happening. Let's say it's a very simple category, actually. Just a single object with an identity. Okay? And we say we have another category here, like this. This is our second category. So there's actually only two functors possible, right? You know, these two have their identities, right? the two functors are obviously the one that sends this object here and the one that sends this object here. Right? This is the only way, I mean, an object cannot be sent to more than one object. It can only be sent to one object. So if the category D has two objects, this is how it's going to be. And
oh, I see. Okay, so a functor cannot map one object to multiple objects.
yeah, no, cannot. An object must be mapped to another object. Yeah.
Okay.
And composition is preserved in a trivial sense because the only relevant arrow is identity, and identity is preserved. Identity.
Yeah, everybody has the identity arrow. So.
Yeah, and if you compose identity with identity, you get identity back, which is
Identity.
true. Yeah. Okay.
If
So
you compose identity with a different arrow, you get the different arrow, right? That's the thing, the rule, if I remember correctly.
exactly. Yeah.
Composition of identity with a non-identity arrow, the result is the arrow, the other arrow.
Exactly. Yeah, in both directions. Yeah. So, like, yeah. So a natural transformation is simply a map this way. Choose another color here, maybe just white. Yeah. Okay. So it's a map between
Functors themselves.
yeah. Okay. And the way we interpret this square is that for any f from A to B in the original category, so in this case, A is this one object and B is also the same object, and the only f possible is identity, right?
Mm-hmm.
So let's write that here. A to A, identity. That's the only map possible for this condition, A to B, right? Then let's write out the thing. So f of A, f of B, f of F. So let's do the left side here, right? That's everything that F sends to. So let's close this. I'm going to call this one A, and then I'm going to call this one 1 and 2. Okay. So in this case, f of A, I'll use the color, corresponding color, f of A, f of F, and f of B, right? So actually, this is f of A again, because there's only one object. Right? So this gets sent to 1. This is equal to the identity on 1.
Mm-hmm.
And this is also equal to 1. Right? So that's the left side here. So we have, let's draw it right now. Look at this. Okay. Then G is similar, right? G is just 2, identity 2. Okay, now we're almost there. And then alpha A, this is the natural transformation itself. So we call this alpha of A the component of the transformation at A. So that's alpha A is this. And also because the bottom thing is also A, this is also alpha A.
Mm-hmm.
So this is the condition. So,
Thank you.
Yeah. What this means is that if I take 1, which is f of A, and then I go across with the alpha of A, and then I go down for F, which in this case is the identity, it's the same as if I went down from F of A to F of B. In this case, it's the identity again. And then I did the alpha of B, which in this case is alpha of A, right? In a very trivial sense, this A becomes A, so it's very easy to see this is true. But in the more general case, right, A is B, so it's alpha B. The identity is just some function, and this is B. This is A. Sorry, F of A, F of B. A, F of F, F of B. Right, this is what the general case is, but we just chose things in such a way that's like very trivial to see the naturality. Another way to think of it is that your category looks something like this, right? It's like a complicated graph structure of some kind. The functors are like painting or sketching or something on top of the category. So if I have a category that looks like this, a triadic thing looking like this, I'm targeting or selecting an image in the codomain category. I could have selected any other three to be the targets, right? Any other 3 points here. But let's say I just happen to choose these 3 points. And then I had another functor that's selected like so, right? And then again, it's not this, sorry, these 3. Right? So in this case, my domain is here. This is my, actually I should use D for domain, C for codomain, right? And I have 2 functors here that are like 2 copies of my domain inside the codomain, 2 pictures of it. The natural transformation tells me for every object how I need to go to make the image of one look like the image of the other. So the natural transformation is this, right? This becomes this, this becomes this, this becomes this. Right. Okay. Let's see, and then we can go higher even. So like natural transformations themselves are composable. So then you get something crazier, like, you know, I won't draw it completely out, but the same way that we had this square with a single natural transformation, and we have alpha A and alpha B here, we can extend that by saying another natural transformation beta something, beta, I guess, maybe this is also beta A, beta B. Yeah. So this is like saying, right? If these three arrows are all functors again, from a very simple category identity, then we can compose them just as we found a way to take, this is alpha of A, to take this here. We can also form a beta. Yeah, I guess it wouldn't be A here, it would be whatever this is called. Oh no, and actually this is alpha A, because this is A here. Yeah, so we can compose these to make a new natural transformation. Yeah, seen in this way, it's like natural transformations, if it's going from a functor of a single object only, this is just normal composition. But there are more complicated cases, right? And so we can form a new category called a two category, where functors are called one morphisms and natural transformations are two morphisms. And then, so that's basically this thing that I drew here, where for any object, so for any categories, category C and category D, you have F and G. And then the two category, which we can think of as a surface, sorry, the two category is this plus the natural transformation, which is considered a surface. Right? The points are one-dimensional, sorry, points are zero-dimensional. Morphisms, one-dimensional. And then this one would be a two-dimensional. Yeah. And then this notation is a category consisting of functors from C to D as the objects. So this is kind of related. In this case, F and G are considered to be the objects. So in the functor category, we write this way. This is F, and this is G. And then the natural transformation, let's call it, let's call it B. It looks like this, right? So these two are two different ways of describing kind of the same thing. This is a two category, and this is a functor category.
Like functors become objects themselves.
Yes.
So why do they call them functor? Why not just arrows? Like, are they like a structural difference between functors and arrows?
Yeah, so arrows, they don't have this composition preserving quality. That's what makes something functor. And you will actually hear mathematicians say that some phenomenon exhibits functoriality when you can find a functor that follows this this formula here, because there's something about composition that's special that you don't find in other structures. But as with a lot of things in math, like you can usually find different representations of the same thing. So yeah, you can turn a functor into just an arrow, exactly like we did here, right? And the two category of functor is just an arrow. It's just a thing, right? But then also you can think of it as an object in the functor category. So functors, morphisms, objects, they're all interchangeable depending on the resolution you're looking at.
Exactly.
Yeah. What's important is this condition though, this composition preserving property.
Now, functors are not does not have transitivity, do they?
They do, yeah, because of this. And that's what you mean, like by transitivity. I mean you can compose them together.
Right. What I'm saying is, if instead of lowercase fgh, we had uppercase fgoh, f follow functor f follow functor g functor h, is it equal to functor f follow functor g and then the whole thing follow functor h?
Yes.
Is that true?
That's a good. Yeah, it's true. Yeah, that's a good question though. Yeah, I didn't cover that. But yes, functors also have obey associativity and composition.
Sensitivity. Okay. Do natural transformations follow that?
Yes. Natural transformations also do. Yeah, like in this case here. This is what it looks like for natural transformations.
So functors really have one condition that arrows don't have, which is that one on the next page.
Yeah. Yeah, this is the important thing, and it's so general. It looks very simple, but it's very powerful. Yeah.
Right. Now, do natural transformations follow property number one? If f was alpha, is alpha of capital F follow capital H equal to alpha of capital G follow alpha of capital H?
Yeah, so that's a complicated question because actually the notation for natural transformation is not alpha of big F. You never see that, or I've never seen alpha of big F. I see alpha at A, alpha at B. So it's a point-wise definition of natural transformation. But this, in the spirit of your question, though, I think yes, it does preserve composition, but in a way that you can see very clearly in this square here.
I see.
Yeah, because it will carry the objects in such a way that this always commutes. Yeah.
So natural transformation, the domain for natural transformation is not the functor, but still the object.
Yes, still the object, but it's in some sense between two copies of a image. Between two
objects,
copies, yeah,
of the objects that are the domain of the natural transformation is the codomain of a functor.
Yes, exactly.
And the codomain of the natural transformation is also the codomain of the functor.
Yes, that's a good way to say it, yeah. Yeah, that's exactly what this color picture is, yeah. Yeah, the wherever the codomain of the functor is, that's kind of the image of some category, and then you have another image of some category.
Yeah, that's why you have coloring only on the objects of the codomain of the functors.
Yes. And then in a more complicated case, you would have alpha of A, alpha of B, and so on, right? So if this trivial category was more complicated, if it had an A and a B, for example, then our image might look like this. Then, I don't know what color I used for this one. You would have alpha of B here. So your natural transformation would be defined by a set of arrows, changing each object of one thing into the other, right? So this, in this case, was like this, this sent this over here. I don't know if you see that, like,
yeah.
Yeah.
So green or red are functors, but wait a minute. How can you map it to, no, hold on. The red is not right. So you have to put one of the red arrows to B.
Yes, you're right. Red arrow should be like this, right?
Yeah.
Exactly. So I see we have an image, a green image, and a red image, let's say, of our original category. And the natural transformation, point-wise, defines a way to get from the green image to the red image.
Yeah, okay. That also explains what, why.
Sorry. Go on.
No, I was just saying that this makes sense that it's a space because it's like a projection of points and arrows from one dimension to two dimensions because it replicates the dimensions.
Yeah.
It looks like the natural transformation says why one functor is an image of the other, in a sense.
Mm-hmm.
Like
Yeah.
I think it said something to that extent a while back. I thought it was a good way of making intuitive the idea of a natural transformation, because this second degree morphism between morphisms sometimes get kind of tricky to keep in mind. But the idea that you have a way to make explicit the why is there a structure that is mapping another one? So you are kind of mapping the mapping in a sense.
Yeah, you're mapping the mapping and you're showing that exactly there is some consistency in one mapping that is preserved in the second mapping. Now, the key here, though, is that natural transformations can collapse things, just like we've talked about with morphisms and with functors, right? Collapsing in this case would be alpha of A could map both of these here, right?
Yeah.
Why is this still a natural transformation? Because composition would still be preserved. Because identity composes with itself. So it's kind of in a trivial case, right? So natural transformations don't necessarily have to be like preserving the points.
Interesting.
Yeah. So, but you kind of limit what's there because like although natural transformations and functors can collapse points, they can't make new points, right? So if you have a category and you have a bunch of points here, some information, right? The information of a category is expressed by the set of all of its arrows to each other. Yes, I can collapse this. I can collapse this down to a single object, or I can collapse this down to two objects, or so on, right? I can do different types of losses of information. But there's an upper bound to this, which is if I at most, sorry, there's a lower and an upper bound, right? The lower bound is a single constant functor. The upper bound is an isomorphism.
Mm-hmm.
I collapsed everything to a single point, or I mapped everything point by point, exactly preserving their compositions.
Mm.
Yeah, so all the arrows and stuff are preserved. And the same thing applies for natural transformations. I can preserve the images of two different functors exactly as they are, just, you know, kind of rearranging them, but the total information content's the same. Or I could lose some information, but the lower and the upper bound is the same kind of idea.
So given this, can you explain to me why Badiou, when constantly moving from the category of sets, which is the poset,
Mm-hmm.
to the actual appearance,
Mm-hmm.
which is a geometrical thing, uses the name function. Whereas when he goes from appearing to sets, uses the name functor.
So I guess the question is, when does he go from sets to appearing? Sorry, when does he go to sets to
Like,
transcendental?
No, transcendental is the set because it's a poset.
Yeah, okay. But so is the ontological support, right? Some multiples are also sets.
Yeah.
So you could say, yeah, Badiou does work sets to posets, yeah.
No, hold on. So from transcendental, which is a poset,
Mm-hmm.
which is a set because it's a partially ordered set.
Yeah, okay.
He goes to objects and atoms and elements and things like that, which is in the world of appearing. So he says that this region of the appearing, this region of the painting, or this section of the demonstration has the transcendental index of blah.
Mm-hmm.
Right. So he calls it function when he goes from appearing to transcendental.
Mm-hmm.
You're right. So the domain, for example, for the transcendental indexing function, the domain is the appearing, is the painting, and the codomain is the transcendental. And he calls that transcendental function.
Yeah, I read it as not from the domain is not appearing, domain is being.
Well,
so identity, okay. So identity actually in its most native form, it looks like this, right? It's two free variables. And it maps from set down to transcendental, right? You take an element of a set and another element of a set, and you say how identical they are.
But transcendental is a poset, so it's a set to set. It's
A
times B to B to T.
Yeah. Well, we could say T is a kind of a so it belongs to the category of sets. It's a kind of set. Yeah.
It's a kind of set.
Yeah.
Now,
but it has some extra structure on it.
Right. So he calls this the function, the transcendental function, which is
indexing.
Which is not a terminology, at least according to your review, a terminology belonging to category theory. There is no function in category theory. There are arrows and there are functors and there are sheaves and stuff like that. There's no function. Right? Now,
well, there's functions in the category of sets. So it depends on what category. If you move to the category of groups, then the morphisms are called group homomorphisms.
Okay, so let me form my question another way. Let's finish the thing. Now we have a functor, right?
Yeah.
I already forget how he writes the functor. We have functor of object A.
So yeah, given some t and given some a, we have a functor from t to a called fa.
Right.
Yeah. So in that sense, it's t to a.
T to a.
Yeah.
Okay. So which is opposite to the other one? Now,
kind of. It's not exactly opposite because
I mean, instead of ID, if you write E of
right.
E of A, it would be opposite to that, right?
Yes. E, we can write it this way. It goes from set to T, yeah.
Right. So can you, like, given these, like basically two sets of things, can you tell me, using the terminology that we have so far, what is he doing? Are these functors? Are these, what are these? Are these natural transformations?
Yeah, it's still at most a functor. Natural transformations will come in when we go between objects. So relations can be, in some sense, like a relation between object A and object B, can be thought of as a morphism between two functors. Because they're a morphism between two functors, they are natural transformation, right?
So basically, in general, in category theory, if you go from one collection, one category, which is one collection, like so to speak, collection of points and arrows, to another collection of points and arrows, we call it a functor. So in this case, we are moving from one collection, which is the collections of shapes or collection of people and relationships or whatever, to another collection.
Yeah.
So in this case, it is a functor.
Yes, because there's some relations here that need to be preserved.
Correct.
But however,
gotcha.
in the first case, this identity, the reason this is not a functor, even though it also takes stuff to some collections, right, is because he has not yet defined a structure on sets corresponding to the compositional structure of, right? Composition means we need something like this. We need functions, and we need to say that for any two functions like this, we can make a third function. That doesn't exist right at the beginning. All he has is just a bunch of different sets.
But later on, do we get something like this? C is a category and D is another category. So in this case, a couple that A comes from C and B comes from D.
Yes. So two different objects.
From two different categories.
No, it would be from the same category.
So we don't have such a thing across two categories.
Yeah, okay, I guess technically the same category twice. Yeah. So a relation, which we haven't gotten to yet, but it will be the next meeting. A relation, you can say, takes world times world to some new thing. So for every two worlds, we have some new thing called a relation. Or we can say maybe set of relations.
I'm going ahead of myself. So let's just finish what you wanted to finish.
Okay. Yeah, I think this is pretty much it. I mean, I think we just need some time to let this sink in with categories, functors.
Did you post this anywhere? Did you post your presentation or not yet? You will do it
not
later.
yet. Yeah, I will do it probably this weekend because last time it wasn't ready yet. So
it's a rough shape. I know, I get it.
Yeah.
Like if you post it in our public page, you can upload updates, or you can put it in the, not in the public page, but in the page that in the document tree that Gabriel created.
Yeah, either one. I think I'll probably post it on our website. Yeah,
Okay.
Maybe it'll be my
Sounds
note
good.
for this section. Yeah. So actually, all of this stuff that I presented today, I wanted us to get to this point where we can understand the Yoneda lemma. But I think that's going to be another hour at least. So I think we should stop.
Okay. So you're starting with Yoneda lemma next time.
Yes. Yeah. We'll start with Yoneda and go to the end, hopefully.
Yeah.
Yeah. This is everything we need to talk about worlds in category theory.
Great.
Sounds good. Excellent
Right.
work, man. Excellent work.
Yeah.
Thank you guys
learned
again.
a lot.
We keep
It's
the meeting.
amazing. Thank you very much.
We
Thank
keep
you.
the meeting on Tuesdays like normal next week. Tuesday 9 p.m.
I think so. You're okay, JP, for next Tuesday?
Yeah, I'm okay. It was kind of an domestic emergency.
I forgot to ask. Everything okay with you?
Yeah, no, things are fine now.
Okay, very good. Very good to see you guys. Although we don't get to see you, Dennis, but
Yeah.
We'll never get to see
very.
that.
I'll
very
turn on
good
my
to-
camera next time. Yeah.
Okay, guys.
Okay, take care. Have a good night.
Yeah. Take care. Sleep well.
Bye-bye.